Okay. So today we're going to continue to try to finish up the discussion of the two laboratory experiments, the differential liberation and the constant volume depletion test for reservoir fluids. Is there any questions about the discussions we had about the constant composition expansion test or the multi-stage separator test, which was kind of the first two that we talked about? Any questions about those? Okay. Then we got started on the differential liberation experiment, which is the main test for oils, reservoir oils. And the intention of that test is to measure properties of the oil and the gas that comes out of solution from the oil, namely the density of the oil as it loses gas coming out of solution, and the gas properties, the density of the gas itself, the viscosity of those two phases, oil and gas viscosity, and then how much the oil shrinks was an important property of this test. And then the amount of moles or quantity of gas, the volume of gas that comes out of solution. And these are the main properties that are measured. So. Okay. Now, we went through the first stage of the differential liberation experiment, which typically is somewhere between 5 stages of depletion and maybe as many as 8. Theoretically you could have 10. Probably 8 is about the most I've ever seen, where you remove the gas each time. So we start with the system at the bubble point pressure. You lower the pressure at reservoir temperature, and a gas phase evolves. It's brought to equilibrium, and then the gas is removed as pressure is kept constant at, in this case, P2. Remove the gas, we measure its volume, we measure the amount of moles removed, and then we can calculate the Z factor of the gas. And of course, from the Z factor, we basically can calculate the density, which is just the pressure times the molecular weight of the gas over the R, T, and Z term. So the molecular weight of the gas would come from either the measurement of its composition or the measurement of its specific gravity or directly molecular weight measurement. So either with the composition, in which case you just average out the molecular weight of the gas using the component molecular weights, or they could actually physically measure the molecular weight. So these are so then starting with this second oil, if we call this the first oil, we basically bring this next oil as their starting point. Oil 2, still pressure 2, and then we bring it down to a lower pressure and just basically repeat the same process. The oil shrinks further. This gas is then removed, and we get the properties of the gas, the volume of gas removed here, the moles of gas removed, and accordingly the Z factor of that gas, its density. And then I told you that we needed the gas viscosity, and that's not measured directly, but the viscosity of gas is usually calculated at each stage. And it's calculated from a correlation, typically a correlation that's a function of gas density I believe, and reservoir temperature. And this correlation is called the Lee-Gonzalez, and I believe it's given in Chapter 3. It's not particularly important that you read it or look at it, but that's typically the equation that's used by most laboratories. And they don't measure gas viscosity because it's, well, first it can be well predicted with these correlations within maybe 5% normally. But the equipment for measuring gas viscosities is not, at high pressures, is not particularly simple equipment. So they basically just don't do it. They don't measure those viscosities. So it's calculated. So this is all the gas properties here. We also, in today's PVT reports, you'll get the composition of that gas. Now, one of the problems we alluded to last lecture was that when they flash this gas to the surface conditions, they either ignore or they don't collect all of the liquid that condenses out. So basically this is kind of a big uncertainty in getting that right in the laboratory. The laboratory is not really set up to do this properly, to get the exact gas composition. So even if they report this, you should be a bit skeptical to the amounts of the let's say C5 plus the heavier components that would form the condensate. Probably we didn't collect all of the condensate that fell out during the flash to standard conditions. Probably too low. So the gas that they report probably is too lean in a sense.
Gas deviation factor.
Yeah.
So for the calculation of this at G2, we need this number of moles of the gas.
Right.
And how do we get this?
Yeah, you either run it through a gas meter. When it flashes down to standard conditions, there's like a gas meter. It just measures how many cubic cc's flash through the gas meter.
And then convert it.
And you convert that, being at low pressure, you can convert that to moles with the 23.68 number, something like that. Or I think in the old days they might have collected some of these. They would evacuate a glass bottle, and they would fill that with the gas until the pressure reached short of 1 atmosphere, because otherwise the glass would explode. So they would literally measure the weight. You had the evacuated empty glass bottle, and you had the glass bottle with the gas. So you got the mass of gas connected, and then knowing the pressure increase, you could get the moles. So then you actually got the molecular weight from that directly. There's different ways, and I don't know what the current laboratory procedures are. Some of these are probably so old that they don't use them anymore.
But we can also do it like if we know the cell volume of the gas and we know the surface volume of the gas, standard condition volume, we just divide them and we get the Z factor.
You're assuming that there's no condensate? I mean, the Z-factor calculation would be, as I've shown here, and that requires you to have all of the moles of gas removed. So if you're missing some there, obviously it'll be off a little bit, but you basically get the moles of gas by direct measure, either through a gas meter and then you use this equation here. And then this oil shrinkage is oil volume here at P3 and reservoir temperature. Now, I told you that we need the oil density and we want the oil viscosity. Okay? We've got the oil shrinkage. That's by direct measure. The oil density is calculated. Okay? So this is calculated by kind of a material balance. I'll show you how that's done. We know the gas that we took away, so we know the mass that was taken away, and we kind of we do a material balance of all the gases that, I'll show you how we get that a little bit later. Because we have to complete the entire experiment before we can do that calculation. Okay. The oil viscosity is actually measured directly, but in a separate parallel experiment. Okay, the same kind of procedure. So it's actually measured in a separate, I'll call it parallel differential liberation test, where basically the depletion is going on in not a PVT cell, but in a viscometer cell, a high pressure viscometer. So you kind of conduct the experiment within this viscosity cell. Now, there are new types of viscometers, so they may not do it that way anymore. They may actually take some of the sample here and measure the viscosity directly. You don't need to worry too much about the exact details of how they do it. But this measurement is probably at best within about 5% accurate, and at worst it's probably in the 15% range of accuracy. Okay? For different viscometers, different methods, different laboratories, that's probably as good as you're going to get. So this step here is repeated multiple times, anywhere from 5 to, let's say, 8 times. But then we're going to look at the last stage, pressure N-1 down to atmospheric pressure. Okay? Because this is done a little bit differently. And what happens is that we come in with the oil, and that pressure may be typically 10 bar to 15 bar. Okay? 10 to 15 bar. This is our oil at this next to the last stage. And then what happens is that we max out the volume of the PVT cell. The oil has done some more shrinking, but we haven't reached standard pressure because we max out the volume. And there's this gas that comes out, it's basically behaving like an ideal gas, so it takes up a lot of space. So you max out so this basically reaches the cell reaches the max value. Okay, and we're still somewhere in pressure here. So then they typically they'll have a valve, and they'll collect the gas, but they'll basically bleed off the gas. And as they do that, the pressure will eventually, reach 1 atmosphere, and you'll get this final oil. Okay? So we're doing this bleeding process. So this might be at 15 bar, just as an example. I don't know, maybe it reaches 5 bar before it maxes out. I don't know. But at some point, and then from 5 bar down to the 1 bar, this gas will be bled off. Okay? So that's kind of how it works. This process is not the same as if we went from that oil at N-1 to this really big volume. Which we don't have the volume, and we'd get a different final oil volume here. Okay? So the main difference is that these two oil volumes, this is down at 1 atmosphere, these two oil volumes here are definitely not equal. Okay? The moles of gas that comes out will be similar. I mean, it'll be different, but the biggest effect will be on that oil volume. Okay? Now, the final oil volume in the laboratory will then be cooled from 1 atmosphere. This is all at reservoir temperature, right? This is all at reservoir temperature here. Then they'll cool this down to standard 60 degrees Fahrenheit. What will that do to the oil volume? It'll kind of get a little bit smaller. Not very much, but maybe 4, 5, 6%. And this is what we refer to as the residual oil volume. That's the residual oil volume. Okay. If we took this would be flashed at 1 atmosphere. So if this is all just a single flash, not a bleeding process, okay, and then we cooled it down, okay, this would be a different residual oil volume. I'm going to call this flash, and I'll call this B for bleeding. Okay? Yeah.
In the first case, when you took the sample from 5 bar to 1 bar?
Yeah. You're continuously taking gas away from the cell.
Okay, it's just not shown in the...
It's not shown. You're just, it's just, you have a valve and you just take the gas away and the pressure slowly drops.
You are measuring the volume of that.
You're measuring the volume of the gas. And again, the amount of gas that you would receive in a single flash here, and the amount of gas that you get in the other, the amount of gas will be similar. Okay? I mean, it's not going to be the same, but similar. It's not such a big difference.
But oil will be less in this.
But the oil volume is going to be different. And I'm going to tell you why. I'm going to try to explain why that volume is very important. Okay? It being different. Okay. All right. Anyway, that's the experiment. So now we've got all these numbers that we've been measuring, and I'm going to explain what's actually reported in the PVT. So in the PVT report, what do we get out? Okay, so as a function of pressure, well, let's just kind of summarize what's been measured. Pressure, oil volume, gas volume removed, moles of gas removed. So we could put a delta in front of it, I suppose, just because to mean that it's being removed. What else did we measure? Forget the viscosity, it's a separate experiment. We've got the
Calculate and see.
okay, but I want to stick to what's actually measured. So we might actually measure the mass removed as well, so that would give us molecular weight. And then the composition, with this uncertainty to it. These are the things that are measured. These are both dependent on pressure and temperature, so they're at the particular pressure and reservoir temperature. Of course, molds and mass composition doesn't matter what the conditions are, but they reflect what the gas at the pressure temperature. Okay. So now that's what's measured. In addition to that, we have what's measured is this final. Yeah. God for that. We also have this final residual oil volume, which I called B. All right? Can you guys see that? I have to be a little bit careful of my okay. So what's reported is what we're going to call differential, D for differential, oil volume factor. Okay? And that's equal to the oil volume divided by this residual thing. Okay. The oil density, and there the equation's a little bit too complicated to put here, so I'm going to put the oil density equation down here. This is calculated, and it's the final mass of that residual oil from the bleeding. We'll actually weigh it, so many grams, and then we add back, starting at the very end, the last stage of gas removal. So if we're looking at the, well, let's see, let's not call it K here, let's call it something else. Stage. And we're looking for the density at stage K. You got the bubble point. Okay. So we take all of the gases that we removed, stage S, divided by, so that's all of the mass. It's kind of the final oil mass plus all the gases that were removed. Okay. To, let's see here. Would this be K plus 1 or K minus 1? K. Let's see. Help me out. At stage 4, we remove some gas, right? But now we're trying to, yeah. But we don't want to put, let's see, stage 4. We don't want to put that gas in with the other, right? At stage 4, the gas that was removed at stage 4. We want to know what's the gas still in solution at stage 4. So I think this is going to be K minus 1, is that right? Somebody give me a nod, yes or no? Help me out here. Okay, we'll say it's right until you figure it's wrong. So this is all. These are all of the gases that were removed below stage K, divided by the oil volume at stage K, which we measured. So the lab does this calculation. Okay. And it should be within probably 1-2% accuracy. They're not losing too much material. Okay? So it should be within a couple of percent accuracy. I'm going to go ahead and put oil viscosity, because even though it's done in a separate experiment, just to kind of put all the oil properties. These are the oil properties for the oil phase. Okay?
Excuse me?
Yeah.
In the last equation, you are trying to get the density in the reservoir.
The oil density in the reservoir at pressure K. Okay?
If
So
you'd like,
let's say that there's 8 pressures. Okay?
okay, if you would like to get the dead oil density, then you will just ignore the delta mg, right?
Yeah, the dead oil density would just be the mass of the residual oil divided by its volume. Yeah. So actually this would be, maybe this would be, maybe this should be n minus 1 to k. I don't know. Look in the book. I should look in the book. Yeah, because the last stage, you don't want to put that gas back into it. So this is going to be n minus 1. Okay? And then if we go all the way up to stage 1, there is no gas at stage 1, right? The first gas that you take away is in stage 2. So this would go to, could it be like that? Huh? It was correct the way it was? Okay. Okay. But it can't be corrected the way it was, because if you want stage N, you shouldn't add any gas. Because, right? If we want stage N, we don't want to add any gas back. So I think we want to, in other words, if that's, should we give up? I think it's in the book. This is going to be a class exercise during the break. Somebody come up and tell me what it's supposed to be at the end of the break, okay? So then, so that's the oil properties. On the gas side, they'll give the what's called the delta RSD. It's how much gas came out of solution. So that's delta NG. And then you have to convert that to a standard volume with our 23.68 number. And that's R TSC over PSC. Okay? Divided by that final residual oil from the bleeding process. Okay? That below there. So I have some room here. Okay? And then they're going to add up at a given stage how much gas is still in solution at a given stage. Okay? It's just kind of summing up these delta RSGs. Then they'll give us the gas Z factor. They might calculate this BG, the formation volume factor, but I'm not going to put it there. They might put that there. If they do, it's the traditional equation being used to convert Z factor like that. If they measure compositions, they'll give those. And then finally, they might give the gas gravity, which is like the molecular weight, effectively, of the gas. And cheating, huh? And then the gas viscosity. It is cheating. I mean, you know, in the old days it was like a few cuss words and, you know, I don't know, just kind of. Okay, so that's basically on the gas phase we get these things here. So so we can go into the monograph, this chapter. We'll go through and try to find these numbers in the tables that are given. Here's the figure. This is the BOD figure. There we go. There we go. Okay. I know I cut off the gas, a little bit of the gas viscosities, but don't worry about that. Okay. So let's just go through here and see. Can you guys read that or not? I need to make it a little bigger. I can do it a little bigger. Okay. So here we've got I'll do in red the gas properties because it's not in the same order as I had. So this is our RSD. This is our BOD. Okay, I didn't put this total relative volume. They've got something that's called, most labs don't give this anymore. That's the BOD plus the BGD, or the BG, times RSD at the bubble point minus RSD. And what that represents is the oil volume plus the total gas volume over this residual volume. So this is the cumulative gas that's come out of solution. in standard cubic, whatever, meters, feet. And then you bring that standard volume to a reservoir volume with the BG, and you add it to the BOD. Anyway, so this is typically not given in laboratory reports, but it is given here, so I'll just put it here, BTD. It's kind of like it might be there, it probably won't be. Here we've got the oil density. We've got the Z factor of gas. This is that formation volume factor, and that's the gas molecular weight, or expressed as a gravity. And then down here we've got the gas viscosity. That, of course, doesn't start until you're below the bubble point, and the oil viscosity. Now, every report, different labs will have different setup. But
It's BG times RSD1B.
no, RSD, that's a D. Right? That's what I give up. Forget the D. I'll leave the D in green. So it's RSD at the bubble point. Okay? That means all of the gas back in solution. Yeah. And then that should read RSD. Just doesn't want to go blue on me. Okay. So that's kind of what's reported. Now, what you see is that the reported BOD and RSD, so these two numbers here, the RSD and the delta RSD, they're basically a function of this residual oil volume, as is this one. That BOD is a function of the residual oil volume. Okay? So, yep. So I'm going to write in red. So you have to, this is what we do in Norwegian. If you're like, wake up, okay? Pay attention. That's what NB means. Does anybody know what NB actually means in Norwegian? Any of you Norwegians? You've seen it before, right? Do you know what it means? Huh? Not bene. Okay, not bene. Sounds Italian to me. It could be, I don't know. Anyway, it just means wake up. Wake up, be careful, be aware. Okay, so that's what it means. So, if you use the DLE data as input to a PVT program, based on an equation of state, okay? And that you will be doing because that's what the industry does today, okay? And the most common one, it's called PVT Sim. It's a Danish company, Calcep. It's the most used PVT program. And there's other ones, lots of other ones. There's the one that I use, Phase Comp. I'm sure no one will be using that out there. There's something called PVTP. It's by petroleum experts, PVTI, Schlumberger, and you get the gist, PVTX, Roxar, Emerson. Actually, this I wrote. And anyway, so there's a bunch of these. If you're going to input the data to such a program, as part of the exercise of tuning the equation of state parameters to your measured data. Okay? All of these programs here, when they simulate the differential liberation test, they will use by default a single flash from Pn minus 1 to Pn. Okay? That's what they're going to do. And that's the volume they're going to be dividing their numbers with. Okay? So let's just assume, as for the sake of argument, from our EOS calculations, it makes the oil volume calculation. And let's say that the lab, if we actually had the measurements, the oil volume from the lab was here. And let's say that these were, every number was exactly the same. Perfect equation of state, okay, the perfect model. 13.62 cc's, 13.62 cc's, okay? 12.45, 11.32, and so forth. All the way down. So we've got the perfect equation of state. But now we get down to Pn, and the equation of state does this flash, and it gets a number here of 5. That was a 5, guys. I know we've run out of time, but when you're having fun, 5.00 cc's. That is as much of a joke you're going to get out of me. Okay, we get 5.00 cc's because it just does this flash down and gets 5, and this one gets 6 cc's because of the bleeding process. Okay? This is bleeding, and this is a flash. Now, when we calculate the equation of state, BOD, versus the lab BOD, even though the equation of state was predicting exactly all of these volumes all the way down here, the perfect equation of state, it's not going to give you the same numbers for BOD, right? Because you have a different process. Now, I've given a difference of 20% here, right? That difference could be 5%, and the difference could be 50%. Okay? So, if it's 5%, you can just say, well, I don't care, or maybe you should care, but you don't. If it's 20%, you have a problem, and if it's 50%, you have a serious problem. Okay? Because what your program is going to try to do, it's going to try to make these two equal. Okay? It's going to try to make those two equal and not the volumes. You may not understand this, but okay. So I'm just going to show you this oil residual volume from a flash divided by the oil residual volume from bleeding. Okay? When are they 1 or close to 1? Well, they're close to 1 if the oil we're dealing with is at a low temperature and if it's a heavy oil. Okay? If it's a heavy oil and at low temperature, these are basically about the same. So if we put temperature here, and we start down here at the lowest temperature reservoir I know is about 80 degrees Fahrenheit. And a heavy oil, we're going to describe it in terms of the API. A heavy oil is like 20 degrees API. I've talked about API, right?
Yes.
Okay, but the Norwegians, they're still confused. The lower the number, the higher the density. Okay? But you have to get used to it, so I'm going to, okay. So a heavy oil, 20 API, its curve is going to look something like this. Now I'm going to go out to the highest temperature I've seen in any reservoir, 200, maybe 200 degrees C. Oh yeah, we're in Fahrenheit. So, sorry, Norwegians. 350 degrees Fahrenheit. That's hot. That's a hot reservoir. You got some in Hungary, for example, here in Europe. So this thing is going to go like that. And then if you get to high enough temperature, this thing is going to kind of start turning over a little bit. This is for a 25 degree API oil. Okay. If you take North Sea type oils that are like 30 to 50, 30 to 45, then you're going to start seeing things like this. Okay, so that might be a 35 degree API. Now you have to get the lower scale down here. This is not 0.99 down here. This is like probably 0.5. So if you get a light enough oil, like 42 degrees API, that would be, I don't know, there's not too many like that, but maybe Smørbuk Sør, something like that. And a very high temperature, 300 Fahrenheit or something, then this thing is going to pass a factor of 2. So lighter oils. So basically, if this ratio is, if it's, I don't know, less than about 0.97, that's 3% error, you should be concerned as a good engineer. Okay?
Concern meaning you go back and retweak.
You go back and you try to do something to avoid this problem. Okay? You go back and try to avoid the problem. So, different programs allow you to handle this in different ways, but by default, if you just put the numbers in, you're going to get a problem. Okay. So, what you want to do, the best thing you can do, is to basically take the equation of state program and between p n minus 1 and standard conditions here, just add 5 to 10 steps of differential depletion. Okay? Just artificially. Go from, what was it, 15 bar, go to, the first step might be 10 bar. Then you go 10, 9, 8, 7, 6, 5, down to 1. Okay? That's simulating something similar to a bleeding process. So you basically try to simulate bleeding. Okay? And what that'll do is that'll bring that maybe not to 6 exactly. We have the perfect equation of state, but it's an approximate. So this might be 6, I don't know, 5. Maybe not 6. Maybe it'll bring it to 5.92 something, which is like 6. So that's what you can do. Now the thing is, I'm going to give you a break, but if you use DLE data as input to a PVT program, today's world, that's going to be, if you do anything with that lab report, if you do anything with it, that's what you're going to do. Okay? So it's like a 98% chance. If you do something with the report, this is what you're going to do. which means that probably understanding this is the most important thing I'm telling you about this report to avoid this problem. Okay? The solution is this is the solution here, and it's relatively easy to do. Now, after the break, I'm going to tell you what the old school people had you do with the differential liberation experiment test data. Okay? The old school, which very few people do today, but I have to tell you about it because I'm old. Okay? All right? So we'll take a break, take a 15-minute break, and then we'll